In the previous lecture, we have discussed in very detail an important effect which is called Meissner Effect. And in accordance with Meissner Effect, a superconductor completely ejects out the magnetic flux and the magnetic field inside a superconductor is zero. But is this a practical situation in real sense? Answer is no. Actually, a superconductor behaves like a perfect diamagnet. It is experimental fact. The magnetic field inside the superconductor will be zero. It is also an experimental fact. But there is no penetration of magnetic field or magnetic flux inside a superconductor is not an experimental fact. Actually, in practice, it is found that the magnetic field penetrates to some extent into the surface of a superconductor. Okay? And the distance up to which the magnetic field penetrates into a superconductor, that is called penetration depth. Okay? So definitely the Meissner effect needs some modification in accordance with practical point of view. Some modification must be done over this Meissner effect. Okay. So to account for the penetration of magnetic field into the surface of conductor, we must modify Meissner effect. Okay. Actually, it has really been found that the penetration depths are much larger than the atomic distances. Okay. And in order to explain this penetration, it is desirable to modify a consecutive equation of electrodynamics, which is actually Ohm's law, rather than we modify the Maxwell's equations. So you can say that whenever we talk about the electrodynamics of superconductors, okay, electrodynamics of superconductors, then we must modify the Ohm's law, that is J equal to sigma E. This law must be modified. Actually, J equal to sigma E, this is called microscopic form of Ohm's law, and this law is obeyed by a normal conductor. But if your aim is to apply this law to a superconductor, it needs modification. In its original form, this law does not apply for a superconductor. Okay. Actually, this problem was solved by a scientist named London, and so in this present lecture we are going to see two equations provided by London after the modification of this Ohm's law, which are actually called London equations. Or you can also say, in present lecture we are going to see the discussion of electrodynamics of superconductors. So whenever you talk about the electrodynamics of superconductor, that means you are talking about London equations. So actually in this first part of the lecture on London equation, we will talk about the DC field, that is not the time dependent field but the constant field. But after this lecture, in a subsequent lecture, we will also see what will happen when we talk about the AC field. Okay. So first of all, we are going to see here the discussion on the derivation and explanation of London equation. So let us see how we can find this London equation and what these London equations actually refer, and how we can explain the penetration depth that is the penetration of magnetic field into the surface of a superconductor by the help of these London equations we will learn in this lecture. Okay. Actually, as I have told you, if you want to know about the penetration depth or about the supercurrent, then you have to modify Ohm's law, okay, not Maxwell's equations, because you already know that Maxwell's equations are not adequate to explain the electrodynamics of superconductors. That is, to account for the conditions E equal to 0 and B equal to 0 together. You know, you have just learnt in the previous lecture when I have discussed the Meissner effect that a superconducting state of a material is described by these conditions. That is, if E equal to 0 and B is also equal to 0 at the same time, then such a state of material is actually a superconducting state. Okay, so Maxwell's the equations do not agree that when E is equal to 0, then B will be also 0 together. On this fact, Maxwell's equations do not agree. So we simply say that the London equation can be found not by modifying the Maxwell's equations, but we can derive it by the modification of Ohm's law in vector form. That is J equal to sigma E. When this law will be modified, we will get two equations, and those equations are called London equations. Okay. In fact, as you can see, I have written London in 1935 derived two field equations to explain the superconducting state of matter modifying Ohm's law. Mark it. Okay. Actually, whenever you talk about the conductivity of superconductors, as you know, in case of normal metals, there are free electrons which is responsible for its conductivity, which those electrons are also called conduction electrons. But whenever you talk about the conductivity of superconductors, actually in that condition, there are two types of electrons in our material. And those two types of electrons are called normal conduction electrons and superconducting electrons, or superconduction electron you can also say. In fact, these two types of electrons are not very different. They are the ordinary electrons, but the electrons in a particular range of temperature behaves as a superconducting electron. In fact, the way in which the entropy varies with temperature, that actually suggests that the number of normal conduction electron decreases below the transition temperature, while the superconducting electrons increases. It means if you are talking about a specimen or a material, then when the temperature of that material is greater than Tc, where Tc, you know, it is called transition temperature or critical temperature, then actually the number of conduction electron, normal conduction electron, which we denote by the symbol this Nn. Okay, this is the concentration or the density of normal conduction electron. Actually, this will be much greater than the concentration of the superconducting electron Ns. Ns represents the number of superconducting electrons per unit volume, and this Nn represents the number of normal conduction electron per unit volume. And when the situation is like this, that temperature of our material is greater than critical temperature, then you know the material behaves like a normal conductor, and in that condition we do not talk about this superconducting electron. But as the temperature is lowered and it becomes less than Tc, then what happens? The situation is just reverse. Actually, in this condition, the conduction, the material is in superconducting state, and in superconducting state, the conductivity of the material is governed primarily by this Ns, that is the density of superconducting electrons actually dominates over the density of normal conduction electron. Okay, so actually this fact has been can be seen by the variation of entropy with temperature, and when we study it, we see that the normal conduction electrons and the number of normal conduction electrons decreases below the transition temperature, while the number of superconducting electrons get increased. Okay, and therefore London, basing on this assumption that there are two types of conduction electrons in a superconductor, namely the super-electrons and the normal electrons, put forward the idea that at any temperature, the sum of the super-electrons and the normal electrons is equal to the conduction electron density in the material in the normal state. Okay, so you can say that if N is the conduction electron density in the material in normal state, that N will be equal to what? This is equal to Ns plus Nn. Here Ns actually represents the concentration of super electron and Nn represents the concentration of normal electron. So according to London, the sum of these Ns and Nn, that is equal to N, which is the total concentration or the concentration of electron in the material in normal condition. Okay, this was this information London actually observed by the study of variation of entropy of the superconductor with temperature. Okay, in fact, as you have learned that at 0 Kelvin temperature, the superconductor consists only super electrons. There is no normal conduction electron when the temperature is extremely low. Okay, but as the temperature increases, the proportion of normal electrons compared to the super electrons increases. Okay, until at the transition temperature all electrons are normal. As you have seen that when we talk about a temperature T greater than Tc, then actually this number of normal electron is much more greater than number of super electron, and we simply say that in that condition the material behaves like a normal conductor, and we do not talk about this Ns. Ns becomes insignificant. We simply say that the material has only normal conduction electron. So we talk about the superconducting electron only when temperature of the material is less than critical temperature. And when you say that temperature is less than critical temperature, it means you are talking about the superconducting state. So whenever our material is in superconducting state, then the material will have two types of electrons, conduction electrons. One is called super electron and another is called normal electron. But when the temperature becomes 0 Kelvin, it means extremely low, then the number of normal electron becomes 0. almost all the conduction electrons present in our material is super-electron, and then only the super current will be present in our can flow through the material. Okay. So in nutshell, you can say that a material has actually two types of conduction electron. One is called super electron, another is called normal electron. And at a temperature below the critical temperature, the density or the concentration of super electron is greater than that of the normal electron. Okay. And at 0 Kelvin temperature, it is completely only the superconducting electron, not any normal conduction electron. But above critical temperature, all the electrons are in the form of normal conduction electron. We don't talk about the superconducting electron. Okay. And now, as I have told you that in this lecture, our aim is to find two very important equations which are called London equation. Okay. And these equations actually are the modification of Meissner effect, you can say. And for this, we will modify the Ohm's law in macroscopic form rather than the Maxwell equation, because the Maxwell equations are not a valid tool for discuss the electrodynamics of superconductors. It deals appropriately the electrodynamics of metals and non-metals, but these Maxwell's equations are not the valid tool for discussing the electrodynamics of superconductor. And so for this, we actually use Ohm's law, and that Ohm's law is modified to get two very important equations which are called London equations. Okay. So let us now see what are London equations. First of all, we will talk about the first London equation. And for this, let us consider that this Ns is the super electron density at temperature T less than Tc. It means this Ns is the super electron density at a temperature less than the transition temperature or critical temperature, you can say. And we also consider that these super electrons are drifting inside the superconducting material at a speed Vs, which is called drift velocity of the super electrons. Okay. And due to the drifting of these super electrons, electric current will be constituted, that is called super electric current. Okay. And this Js represents the super current density. Okay. Then as you know that how this J is related to Vd, if the charge carrier has a charge of minus E, then this is given by minus Ne Vd. Okay. N is the concentration of our charge carrier, minus E is its charge, and Vd is its drift velocity. So the current density constituted by the superconduction electron Js will be given by this formula. Js is equal to minus Ns times E times Vs. Here minus E is the charge of our electron. Okay. Now, as the electron is moving, it experiences electric force, because this electron can move in a particular direction. It can be drifted only when you apply an electric field or the electric potential or the voltage. So if E is the applied electric field across the specimen, then you know the electric force experienced by each electron will be minus E times capital E. E is the electric field. And in accordance with Newton's second law of motion, this force minus E times E will be equal to mass times acceleration. Okay. So this is m times dvs by dt. Okay. And from here you can easily find the acceleration dvs by dt, and this will be equal to minus ee over m. Okay. Now, to get the London equation, first of all, we will differentiate this equation 1 with respect to time. So, after differentiating 1 with respect to time, you will get this djs by dt is equal to minus ns times e dvs by dt. Okay. Now we will substitute the value of this dvs by dt, which is equal to minus e times capital E over m here. So after substituting this, our result is djs by dt equal to ns times e square over m times e. Actually, this very equation is known as first London equation. Okay, and you can see from this result that this equation actually describes the absence of resistance. This equation describes the absence of how this describes absence of resistance. You can easily see. You can see if we take E equal to 0, it means across, let us say this is our specimen. Okay. And we do not apply any electric field across it. E is equal to 0 we take. It means you are not connecting this specimen by any voltage source. Okay, then no electric field will be produced. And if E is equal to 0, you can see from this equation A1, then djs by dt is equal to 0. Mark it. The time derivative of the supercurrent density is equal to 0 when we take E equal to 0. It means when we apply no voltage across this specimen, then djs by dt is equal to 0. And if djs by dt is 0, what will be js? Js will be constant. It will have finite value. So you can say that the equation shows that it is possible to have a steady current in the absence of electric field or in the absence of any external potential. That is, E is 0, but Js is not 0, but it is finite. Okay. Actually, such a phenomenon does not take place in case of normal conductor, because if in case of normal conductor we do not apply any voltage. When a voltage is applied, then current flows and we have current density J. But if a voltage is not applied, V is kept 0, it means electric field is 0, then no current flows through the normal conductor. But what is happening in this case? You can see in this case actually electric field is 0. No electric field means no voltage has been applied across the specimen, but there is a finite electric current. Such type of current is actually called supercurrent. So supercurrent may flow through through our specimen even when we do not apply any voltage. So this is a very remarkable fact which we can draw from this first London equation. Okay. Actually, this is the phenomenon of superconductivity, and how this superconductor differs from the normal conductor. You can see in case of normal conductor, when the electric field is switched off or the electric voltage is switched off, at the same moment electric current will become zero. But in case of superconductor, you can see we can get the electric current without applying any voltage, without applying any electric field. So this is actually the phenomenon of superconductivity. Okay. Now I was talking about the normal conductor, and you have seen that that in case of normal conductor, electric current flows only when we apply a voltage or we establish an electric current inside the conductor. But if there is no electric field, there will be no electric current. And this is evident from this Ohm's law. If you are talking about the normal electric conduction in a material, then the current density is written as Jn. The subscript n has been used for the word normal. So this is normal current density. Okay. And this is given by sigma into A. Or you also call it 1 over rho into A, because sigma, which is electrical conductivity, is reciprocal of the resistivity rho. And from this equation, it is evident that when E is 0, then Jn is 0. So as I have told you earlier, that in case of normal conductor, electric conduction takes place as long as we maintain the voltage, maintain the potential difference across the specimen, or maintain the non-zero electric field. But the moment when electric field will become zero or voltage will be zero, at the same moment the current will vanish. Okay? But the situation in case of a superconductor is different. A superconductor can carry supercurrent even in the absence of any applied voltage. And this is evident from this London's first equation, which have been written in this equation A1. Okay? Because here you can see that when E is 0, then Js is not 0, but it is constant and it has a finite value. Okay? So I think now you have a clear-cut idea of London's first equation. Okay? Now we will see what is the second London equation and what actually we can, what informations we can get from this London second equation. Okay? And for this, let us first of all start with one of the curl equation of Maxwell. Maxwell's curl equation relating E and B is given as curl of E is equal to minus dB by dt. Okay? But you know that this B, which is magnetic induction or magnetic flux density, this B is given as mu naught times H. You know it. Where mu naught, this is permeability of free space, and H is the intensity of magnetic field. Okay? So replacing B in this equation by mu naught H, you can write curl of E. Actually here this cross represents the curl operator. So curl of E is equal to minus mu naught times dH by dt. Actually here the expression B equal to mu naught H has been used. But mu naught is a constant factor, so it is outside of the differential operator. Okay. Now to get the London second equation, we simply take the curl of this equation A1. Okay. We will take curl of equation A1. So see this equation and then take curl of it. So you can see this will be curl of dJs by dt. So I have written it del cross dJs by dt. Okay. And in RHS, ns E square over m, this is a scalar factor. So when you will take curl, that means curl of vector E. So this is del cross E. Okay. Del cross E. But you can see in accordance with Maxwell's equations, which we have defined here in equation 4, this curl of A is equal to minus mu naught times dH by dt. So let us substitute this value of curl of A here. So this del cross dJs by dt is equal to minus mu naught ns E square over m times dH by dt. Okay. Now we will integrate this equation 5 with respect to time. You can see here dt is present, here dt is present, and you can cancel it. So there will be simply integral of del cross djs by dt. So and the integral of djs by dt, that will be equal to js. So this is simply curl of js, and that is equal to minus mu naught s ns E square over m, and the integral of this dh will be h, and h naught here is actually the integration constant. Okay, this is integration constant. But as you know that Meissner effect prohibits magnetic fields inside the superconductor. You have learned that if this is a specimen, then and it is placed in an external magnetic field, then B or H is 0 inside this specimen. It means no magnetic field is present inside this material in superconducting state in accordance with Meissner law. Okay. So in that condition, this H naught will be equal to 0. Okay. So in accordance with Meissner law, Meissner effect, you can say that this H naught must be equal to 0. And so our equation 6 now can be written like this. This is del cross JH, which is equivalent to curl of JS, that is equal to minus mu naught ns E square over m times h. Okay. And actually this equation is known as second London equation. Okay. This equation is second London. Actually this second London equation explains Meissner effect. Okay. This explains Meissner effect. Now, after knowing the first and second London equation, then by the use of this second London equation, we will be able to discuss the important problem of penetration depth. As I have told you earlier that in accordance with Meissner law effect, no magnetic field is penetrated inside a superconductor, but the actual state of affairs is something different. In practice, it is found that whenever a superconductor is placed in an external magnetic field, then there will be some penetration of the magnetic field inside the superconductor up to some distance. And at the very interior of the material, this field will be 0. But it is not 0 just inside the surface. Okay. Just inside the surface it is not 0. So how actually this how the magnetic field or how this current density varies inside the superconductor, that can be explained on the basis of this London second equation. And for this, first of all, we will have to find the expression for this Js inside a superconductor. According to Meissner effect, this Js must be 0 inside a superconductor. Okay. For example, if you consider that this is a superconductor, okay, then and you plot a graph of distance versus this distance x versus Js. Okay, Then according to Meissner effect, this Js will remain 0. Okay, and when we will inside this material, let us consider that this is just like a sphere. Okay, this specimen, and as you reach to the sphere surface, this current will abruptly rise. Okay, we are talking in terms of Meissner effect, and after that it will again decrease from it will again decrease. So after the surface it will, but after the surface it not decrease, but after above the surface this will be equal to 0. Okay, but at the surface there will be current. Js is not 0, and inside the surface it is again 0. This fact I have told you on the basis of Meissner effect. But is this a real situation? Answer is no. When we will move inside a superconductor, the current density will not vanish abruptly, but you will see after some time that this current density decreases exponentially with distance, but it does not fall to 0 abruptly. Okay, so how much it is penetrated into the surface of a superconductor, now we can calculate it. Okay, and for this we take curl of this equation A2. Okay, this is already in LHS, you can say curl of Js, and now you take the curl of this equation A2. So this will be del cross Js, and in RHS the term is like this. So this will be minus mu naught ns E square over m times del cross H. Now del cross Js, this is just like the vector triple product, and you can see this A cross B cross C. Do you know what is this? According to the definition, this is actually equal to A dot C times B. Okay, and minus A dot B times C. This is just the definition of vector triple product. On the basis of this, you can write this expression as del dot Js del minus del dot del Js. Okay, but you know, divergence of this super current is equal to 0. This is a very remarkable fact. Divergence of super current or super current density is equal to 0. So this first term will vanish, and our result now becomes like this. This is del square Js, del dot del, this is del square, which is called Laplacian operator. Del square operator, you know, this is called Laplacian operator. And that is equal to mu naught times ns E square over m times curl of H. Okay. But what is this curl of H? We can define this curl of H from Maxwell's fourth equation. Okay. In accordance with Maxwell's fourth equation, this curl of H, you know, is equal to J plus dd by dt. Here this capital D is what? You know, this is actually electric displacement. This is called electric displacement. Okay. And J, this is the total current density. When you talk about total current density in case of superconductor, that will be a vector sum of current density due to the normal conduction electron and the superconduction electron. Because in a superconductor, there are two sources of electric current, or there are two types of current. One is constituted by normal conduction electron, which is called normal current density Jn, and another is due to the superconducting electron, and with due to it the current density is Js. So this J is actually equal to Jn plus Js. Okay. But as I have told you earlier that in this present case we are considering the DC field, which DC field, and in the consideration, our consideration is the material is in DC field, and in case of DC field, the Jn, which is normal current density, that is actually negligible. Okay, and this dd by dt, that is the time rate of electric displacement, or you can say that this dd by dt is actually displacement current or displacement current density. So this Jn and dd by dt both will be neglected in case of the uniform field or the DC field. So neglecting this Jn here, you can see this curl of H is simply equal to Js. Okay, because Jn will be neglected and this dd by dt is also neglected in case of DC field. So curl of H is equal to Js. Now let us substitute this value of curl of H, which is equal to Js, in this equation 7 at the place of curl of H. And so del square Js, या Laplacian Js, is equal to mu naught times ns times E square over m times Js. Okay, and this equation can be written as Laplacian Js is equal to Js over lambda square, over lambda square. You can also write this lambda L. This actually represents the London's penetration depth, so we write it as lambda L most appropriately. You can write it lambda. Okay, actually here this lambda L square has been written at the place of this factor, you can see. Okay, and this equation then equivalently can be written as Laplacian Js minus 1 over lambda L square times Js equal to 0. Okay, in fact this equation 9, which is a second order partial differential equation, you can see contains a parameter lambda L, which we have defined in this equation 10. You can check that this quantity lambda L will have a dimension of length. Its SI unit will be meter. And this lambda L is actually called penetration depth or London's penetration depth. Okay, this is the quantity which represents how much the supercurrent will penetrate into the surface of a superconductor in magnetic field. Okay, now as you can see, this lambda L square is inversely proportional to Ns, where Ns, you know, is the concentration of superconducting electrons. And the concentration of superconducting electrons, you have learned, this varies with temperature. As you have seen, if temperature is less than Tc, then this in decreasing the temperature, the value of Ns increases. But when T is greater than Tc, then Ns becomes 0. There is no super-electron in this state. When the temperature is greater than transition temperature, then all the electrons in the material are in normal condition. They are normal electrons. Okay, not super-electrons. So actually the value of this Ns depends on temperature, and as Ns is content here, so you can say that this lambda L will be also temperature dependent. Okay, so this penetration depth lambda L depends on temperature, and it will vary with temperature. Okay, now to know how this lambda L depends on length, how it varies with the distance measured from the surface of a superconductor. For this, let us recast this equation 9 in its one-dimensional equivalent form. Okay, so the one-dimensional equivalent of this equation 9 you can write like this. This is d2 js by dx square. You can see it here. And minus 1 over lambda L square js by lambda square equal to 0. Okay. And you can see this is an ordinary differential equation of this form. This is d2y by dx square minus some constant k square times y equal to 0. This is a most important standard form of second order ordinary differential equation. And it has a well-known solution in this form. You can write Js is equal to a times e to the power x over lambda plus b times e to the power minus x over lambda. Since this is a differential equation of second order, so definitely in the solution of this equation 11 there will be two arbitrary constants. Actually those constants are integration constants. So a and b are actually integration constants, and you know these arbitrary constants can be evaluated by applying the appropriate boundary condition. Okay. Here this x actually represents the distance measured from the surface of the material inside the specimen. So let us see this. If you consider that this is our specimen, then and this point P lies on the surface, and a point here is Q which is inside the surface, and this x is actually equal to this PQ. So this x is measured from surface towards the interior of the specimen. Okay. Now for getting the actual value of Js or actual relation of Js with x, first of all we have to find the actual values of A and B. And for this we will use the following two boundary conditions. The first one says Js equal to J0 at x equal to 0. When you say x equal to 0, it means you are talking about at surface. So we assume that the supercurrent density is equal to J0 at the surface of this specimen. Okay. And you know, as we will move inside the specimen, this supercurrent density must decrease in accordance with Meissner law. And when we will actually in a large depth, in very depth from the surface, then it will vanish. Then it will become 0. So the another boundary condition you can take, that when Js will become 0 when x tends to infinity. It means when you will be at a very large depth from the surface of the material, then this supercurrent density will vanish. Okay. So considering applying these two boundary conditions on equation 12, what will be our result we can see. So first of all, let us apply the first boundary condition on equation 12. When you will take x equal to 0 in RHS of this equation 12, then you can see Js must be taken equal to J naught, which is actually the supercurrent density at the surface of the specimen. So you can see after taking x equal to 0, our result will be J naught equal to A plus B, because e to the power 0, that will be equal to 1. Okay. Now we apply the second boundary condition, that is Js is equal to 0 when x tends to infinity on this equation 12. Okay. So let us take x equal to infinity, and our result will be 0 equal to a e to the power infinity plus b times e to the power minus infinity. But you know, e to the power minus infinity, this is 1 over infinity, and 1 over e to the power infinity is simply equal to infinity, and 1 over infinity is equal to 0. So this second term will vanish, and therefore this is simply equal to a e to the power infinity. And so a is equal to 0. You can see 0 is equal to a e to the power infinity, but e to the power infinity is not 0. Therefore a will be equal to 0. So in this way we have obtained the constant a, and once you know the value of a and then substituting here the value of a, you can get the value of b. And so J naught will be equal to 0 plus b, that is b is equal to J naught. Okay. Now take a equal to 0 in this equation 12 and b equal to J naught, then we get at a distance x, Js means Js at a distance x, this is equal to J naught times e to the power minus x over lambda. Now instead of this Js, you know, we can write this B. This is magnetic field at a depth x, and this is magnetic field at the surface. Because this J is related to B, and so in terms of magnetic field you can write this equation A3 just as I have written in this equation A4. So B naught represents the magnetic field at the surface of the superconductor, and Bx represents the magnetic field at a depth x from the surface of the material. Similarly, this J naught is the supercurrent density at the surface of the superconductor, and Js is the supercurrent density at a depth x below the surface of the superconductor. Now you can easily see that this Js or B actually varies exponentially with x. You can see when x is equal to 0, Js is equal to J naught and B is equal to B naught. Okay. This is actually the maximum value of the supercurrent density or the magnetic field, which is at the surface. Now, as the distance x increases, Js or B decreases exponentially, as I have shown in this figure. Now, if you talk about a particular depth x equal to lambda L, x equal to lambda L, here lambda should be replaced by lambda L because I have considered it earlier. Okay. Then you can see x is equal to lambda L, then this Js will be equal to J naught over A. So in this way, you can define this London's penetration depth lambda L. This can be defined as the value of depth at which the supercurrent density becomes 1 over E times of its value at the surface. Okay. or you can say that Js is equal to 37% of J naught, or this is or B is equal to 37% of B naught. So London's penetration depth is is equal to a distance at which the value of the supercurrent density or the value of magnetic field becomes 1 over E times, or 37% of its initial value at the surface. Okay. So in this way we have this we can see by the help of this London second equation, we can see that actually magnetic field or the supercurrent density just not vanish when we move from the surface of a superconductor to its interior. They do not fall to zero abruptly, but it falls to zero continuously decreasing exponentially. Okay. So I think now you have a concrete knowledge of London equation and penetration depth discussed on the basis of this London equation. But actually there is some drawback of this theory. Although you have seen that this London equation successfully explains that E equal to 0 and B equal to 0, these conditions hold together. And actually when these conditions hold together, such a property is the property of a superconductor. So London theory explains this condition E equal to 0 and B equal to 0 together, characterizing that the superconducting state, but it does not give any insight in the underlying electronic process in superconductor. How actually, what electronic process actually takes place which is responsible for this superconducting behavior, that is not that has not any explanation in this London equation. So you can say that this London equation is not sufficient to know about the electronic process inside a superconductor which is responsible for its character. That cannot be explained. Actually, we will learn in our forthcoming lecture about a very important theory which is called B.Sc theory. I have talked about in very nutshell about this B.Sc theory in my introductory lecture. But in forthcoming lecture, we will see a detailed discussion of this B.Sc theory, and you will learn that actually this B.Sc theory gives a better understanding of the phenomenon of superconductivity, where we will actually take the actual electronic process that takes place inside a superconductor and which is responsible for its superconducting behavior. We will talk about the Cooper pair, and that will explain the superconductivity successfully. Okay, so I think now the concept of London equation, or you can say the electrodynamics of superconductor, will be definitely clear to you. Okay, thank you very much.